Today's topic is dynamic modeling with Euler-Lagrange formulation. The topic, we'll introduce the topic, then we'll discuss about Lagrange's equation, and we will take 6 examples to understand its application. So, start. This is so. What is dynamic modeling? First of all, you have several lectures on previously in this training and learning program. You have several lectures on kinematics. So you know the kinematics is the study of kinetic quantities without considering forces and moments. The kinematic quantities are position, velocity, acceleration, etc. And dynamics, we study motion caused by forces and or moments. So what is dynamic modeling? In dynamic modeling, what we do, we develop mathematical models to predict the behavior of a system. So we correlate, we obtain relationship between these kinematic quantities and forces and moments, so that we can predict the behavior of any system. So these are some robots. I have taken this from this book below. I have given the reference. So in the first robot, you can see that there is a spherical ball. On top of that, some structure is there, and it can move. It can go to some position. It has some operation. But we must know that this is a unstable condition, because in actual case, if you have a rod and if you keep it on the ground, it will fall down because that position is unstable. But how this robot is working, this is not falling down because there is some control system in it which can control and stabilize the system. Then to understand the stability, we must understand how the forces and moments in it are working and how they can be controlled so that the system can be stabilized, so that the structure do not fall. Similarly, you can see in the second picture, we have a robot which has uh, arms and effector. So these arms are connected with each other. We know the how the arm will behave, its velocity, each arm's velocity, acceleration, and position, that can be obtained through kinematic analysis. But how much force, how much torque is required as at each joint, that is the subject should be dealt in dynamics. Similarly, we have in the third figure, we have another robot. So there are other robots you can see below. In each cases, if we want to understand the relation between the kinematic quantities and forces and moments, we need to develop a dynamic model. We need to get equation of motion of the system. Okay. So now we'll talk about I will talk about two approaches. The first approach is the Newtonian approach and Lagrangian approach. So what happens in Newtonian approach? We have here some examples. You can see there are two R robot. There are two revolute joints and two arms are there. Okay, and this robot, these two arms are connected to the ground. You can see that it is connected to the ground, and I have drawn the free body diagram of these two arms separately, side by side. You can see that I have drawn the two free body diagrams, and in the free body diagram, what are the joint forces and moments, reaction forces, everything we have shown here. So in Newtonian approach, what we need is a vector-based approach. So it requires all the rigid bodies to be uh, isolated from each other, which are connected in a system. They should be isolated from each other, and then their interaction forces and moments should be taken care to get the equation of motion. This is something difficult for a very long kinematic chain. So to overcome this, there is an approach that is Lagrangian approach. In this Lagrangian approach, this is an energy-based approach. So energy is a scalar quantity. So this is a scalar approach, and here we need to find out what is the kinetic energy of the system and what is the potential energy of the system. If we could find out kinetic energy and potential energy and the virtual work done by the non-potential forces, then we can find out the equation of motion of the system. That is the basic of this Lagrangian approach. So this is J.L. Lagrange, who was born in Italy and died in Paris, France. So he is known as a great French mathematician who has given us this Lagrange equation. So now I will discuss about this Lagrange equation. So here in the screen you can see one equation, the time derivative of some other quantity del L del Q J dot minus del L del Q J equals to capital Q J N C. J goes from 1 to N. So now here this L, capital L, is defined as T minus V. L equals to T minus V. This is called Lagrangian, where T is the kinetic energy of the system and V is the potential energy of the system, where this small qj are the generalized coordinates. So what do we mean by generalized coordinates? We don't want to go deep into what is the basic and background of this derivation of Lagrange's equation of motion. For the time being, you understand that these qj's are the independent coordinates required to completely specify position of any system or configuration of any system. So number of independent coordinates required to completely specify configuration of a system, that is given by this qj. So suppose there is a 2-degree of freedom system, that means we will have q1 and q2, two coordinates required to specify completely the system's configuration. So how many equations we will have? If we have a 2-degree of freedom system, we will have two equations because the j goes from 1 to 2. So for j equals to 1, we will have one equation. For j equals to 2, we will have another equation. Similarly, if suppose we have 5-dimensional system, means 5-degree of freedom system, then we will have 5 equation of motion. It will start from j equals to 1, j equals to 2, j equals to 3, up to j equals to 5. Okay, this is Lagrange's equation of motion. Now, what is this term QJNC? This term is called generalized force, and this term is related to non-potential forces, the work done by non-potential forces. So suppose there is some dissipation force, say damping is there, so that is a non-potential force. Related to that, some virtual work will be there. So we can find out this generalized force by calculating the virtual work done by that force. So it can be a externally applied force also. In that case also, you can find out part of virtual work done by that external force, and from that, in the below the just bottom of the slide, I have given the equation delta W and C equals to summation j equals to 1 to n. So from this you can get the expression for the generalized force. So now we will take up several examples, at least 6 examples, to understand how to use this Lagrange equation of motion to get equation of motion of any practical system. So our concentration here is for robotic system. We will confine ourselves. This discussion is concentrated on planar motion. What is called a planar motion? A planar motion, one mechanical object or a system of mechanical objects, they move, all parts of there move on a plane or parallel to that plane. That is called a planar motion. So we restrict our discussion for planar motion. We will start from very simple examples so that you can construct equation of motion for that system, we learn it properly, and slowly we will develop up to a 2 degree of freedom system, which will be a robotic manipulator. For that, we will find out, we will determine what is the equation of motion using this Lagrange's equation of motion. So, the examples we are going to take here are these examples. So, I have given them some names: A, B, C, D, E, F. So, there are 6 examples. So, go to figure A, where we can see that there is a spring mass system. So my all these systems which we are showing here are planar motion. For planar motion, all the systems, the motion is in one plane or parallel to that plane. So first figure here at A, this is a single degree of freedom system. Why this is a single degree of freedom system? There is a mass which moves, which can move only in the x direction, and on the it cannot rotate on the plane of motion. Also, it cannot translate above and below the rigid support. The spring here K is a massless spring, and only inertia available here in the mass m1. This is a single degree of freedom system. In figure B, we have a 2 degree of freedom system. Again, the two springs are massless. There are two masses which are moving. So we need two coordinates to completely specify the configuration of the system. These two coordinates are x1 and x2. These coordinates are taken from the equilibrium position of these masses. Also, you can notice these masses are subjected to some force. First mass is subjected to a force, that is F1. And the second mass is subjected to a force F2. Remember that these coordinates x1, x2, they are also function of time. Now moving to another example, C, figure C. In this figure, you can see that this is a 1 degree of freedom system. Why this is a 1 degree of freedom system? There is a rod. We are saying that this rod is massless. This rod is massless, and on top of that, there is a concentrated mass. That concentrated mass is m1. So this rod is hinged at the ground, so it can rotate about the hinge point on a plane. So that means to specify position of this mass, we need only one coordinate, that is theta1. With this theta1, you can completely specify position of this mass, because this rod length is not changing. So the position of this mass is nothing but L theta. This position of this mass can be given by this this length L is known to us and this angle theta 1. Okay. Moving to next example, this next example is a 2-degree of freedom system. Here also these rods are massless. There are two rods. First rod is hinged at the ground, and then at the top of the first rod there is one mass M1, and then from that mass there is another rod, massless rod is hinged. On top of that second rod there is another point mass M2. So here also we have, what is the degree of freedom of the system? The degree of freedom of the system is 2, because for the first mass we need theta 1, and for the second mass we have another coordinate associated with it, that is theta 2. Notice one thing, that in this theta 1 and theta 2 we have taken with respect to positive x-axis, okay, in the counterclockwise direction. We have next example is example E. Here this is again this is a single degree of freedom system, and this single degree of freedom system, but here the mass is distributed in the rod. We no more are considering a massless rod. We are considering a distributed mass system. Here in this rod the mass is distributed, okay, and the degree of freedom of this system is theta 1, and that is given by theta 1. The coordinate is theta 1. Let us move to figure F. Let's move to figure F. In figure F, you can see that this is just extension of figure E, where we have added another rod at the end of first rod, and both the rod will have distributed mass. So this last figure F is a two-arm robotic manipulator, and this manipulator can move in one plane only, and we will find out what is the equation of motion for this robotic manipulator. That is our final goal in this talk. So we'll start with this figure A. This is a single degree of freedom system, as I have already discussed that this is a single degree of freedom system. Why this is a single degree of freedom system? Because we have so arranged the mass M1 that the mass can move only in this direction X, only X direction, original direction. It cannot move in the vertical direction. It cannot rotate on the plane. So among its 3 degree of freedom, 2 degrees are arrested. So one of the degree is available to it, and that is the motion in the horizontal direction, and that motion is specified by this coordinate x1, and x1 is measured from its equilibrium position. We must remember that the spring is massless, it has no mass, it can only resist motion of the mass, and the system is a forced system. The forcing is, here we have mentioned it, F1. Okay, so what is the Lagrange equation of motion for this system? The Lagrange equation of motion, as I have mentioned here, you see just below the figure I have written Lagrange's equation of motion. In this case the coordinate is x1, okay, and in the equation, if you remember, in the equation, Lagrange's equation here, in the Lagrange's equation here, we have mentioned the Lagrange equation. We are using small q as generalized coordinate, but in this case we'll be using small q1 is nothing but x1 here. So this is a single degree of freedom system. We have only one equation of motion. We have only one equation of motion, and this equation of motion is given here. I have written it, Lagrange's equation of motion. To find out this Lagrange's equation of motion, we must define the L. L is Lagrangian of the system. So what is the definition of L, Lagrangian of the system? That is E minus V, kinetic energy minus potential energy. Just beside the figure I have written here, L equals to T minus V. Okay, and so T is the kinetic energy of the system. In this case, if we want to find out what is the kinetic energy of the system, so the motion is here x1, its velocity is x1 dot, half mv square, half mass of the this mass m1 into its velocity square. So that is x1 square. That is the kinetic energy of the system. What is the potential energy of the system? Now the potential energy of the system, what is the source of this potential energy? Source of the potential energy, the energy stored in the spring. Due to the motion of this mass, suppose the mass is moved in the positive x direction by x1. If it is moved by x1, the spring is stretched by x1, then the stored energy which is stored in the spring will be given by half into stiffness of the spring into the stretching in the spring square. So stretching in the spring square, stretching in the spring is x1 and its square. So the potential energy is half k1 into x1 square. Now we can completely define the Lagrangian of the system. So the Lagrangian of the system is given here, L equals to T minus B. Now in the Lagrange's equation, we want to find out what is the first quantity here, del L del x1 dot. Below this, I have written here okay, you can say that this is del L del x1 dot is calculated here, derivative of Lagrangian with respect to x1 dot, and then again you take time derivative of that quantity, that gives you m1 x1 double dot. So in the Lagrange's equation, second quantity is del x1 that we have calculated. Again, differentiating the Lagrangian with respect to x1, that gives you minus k1 x1. Okay. Now here there is an external force. So what is the virtual work done by this external force in the system? The virtual work done by this external force in the system is given by this delta WNC equals to F1 is the force and the displacement is, but virtual displacement is delta x1. So what is the generalized force now? Q1NC. Q1NC will be this F1. How? If we go back to the equation, Lagrange's equation, if we go back, here you can see at the bottom, it is written the work done by virtual work done by these external forces or other non-potential forces is equals to summation of this non-potential force multiplied with corresponding virtual displacement. Okay, so in this case, you see the virtual displacement is delta x1 and the force, external force is F1. The external force is here, the generalized force. And now we substitute all the quantities in the Lagrange's equation of motion mentioned here. So we get the equation that is m1 x1 double dot plus k1 x1 equals to F1. Okay, so this is the this is the equation we have for this single degree of freedom system. Now let us go to the next section. So this is a 2 degree of freedom system. We want to find out what is the equation of motion for this 2 degree of freedom system. So in this 2 degree of freedom system, there are two masses, M1 and M2, two massless springs whose stiffnesses are K1 and K2. So two massless springs are K1 and K2. Now, what is the equation of motion? Lagrange's equation of motion. So below this figure, I have written here Lagrange's equation of motion. Since the degree of freedom of this system is 2, so we will have two equations of motion. These two equations of motion I have written here. And in this, to get the final equation of motion, what we need to do, we need to find out what is the Lagrangian of the system. Again, the definition of the Lagrangian is the kinetic energy minus potential energy. Just below the figure, I have written it. Kinetic energy minus potential energy. What is the kinetic energy of the system? Beside the figure, we have mentioned here the kinetic energy of the system. Since there are two masses and the springs are massless, so this mass m1 is moving at its the velocity is x1 dot, and m2 is moving with the velocity x2 dot. So the kinetic energy is half m1 x1 dot square plus half m2 x2 dot square. That is the kinetic energy of the system. Now, what is the potential energy of the system? Again, the potential energy, source of potential energy is the resistance by the spring. So energy stored in the spring due to this motion. So in the first spring, what is the stretching? Stretching is x1. So related to the first spring, potential energy half k1 x1 square. Related to the second mass, the second spring, what is the stretching in the second spring? Left end of the second spring is moved by x1, right end is moved by x2. The difference between them is the stretching. So difference between them is x2 minus x1. That is the difference. That is the stretching. So the potential energy related to the second spring is written here half k2 into x2 minus x1 square. So now we have kinetic energy and potential energy. Using this, we can construct this Lagrangian P minus P, and that is written here. In the next slide, what we will do, in the next slide, we will substitute this L in this Lagrange equation of motion, which we have mentioned here. There are two Lagranges, two equations of motion are there. In the first equation, first term is the derivative with respect to x1 dot, then its time derivative, and the second term is derivative of Lagrangian with respect to x1, and that is equals to q1nc. q1nc is the generalized force relevant to the non-potential or the virtual work related to this F1 force. Okay, in the next slide, we'll be giving you this. Okay, now here again I have written the Lagrangian. Then one by one we have found the quantities. The first quantity, as I mentioned earlier in the previous slide, that for Lagrange's equation of motion, we have to find out the derivative of Lagrangian with respect to x1 dot. and then its time derivative. So the steps I have shown you here. And then the next term was on the derivative of Lagrangian with respect to x1. Both the derivatives we have shown here. This is for the first equation of motion, and for the next equation of motion, second equation of motion, as we have seen that there were two equation of motion. You can see here there are two equation of motion. In the first equation, it is associated with x1. In the second equation, the derivatives are associated with x2 and x2 dot. So first we have calculated the derivatives related to x1 and x1 dot. Then we have calculated in the next line, we have calculated derivatives of Lagrangian with respect to x2 and x2 dot. So once we have all these quantities, then you substitute these quantities in this equation, Lagrange's equations of motion, and finally here we got the below two equations of motion. These two equations of motion we obtain just substituting these quantities differentiations into this Lagrange's equation of motion. Another thing you can observe, this 2 degree of freedom system figure, below it we have mentioned the virtual work done due to this external forces. So the virtual work done related to the first mass, the motion of this mass is x1, applied force is F1, so the virtual displacement is delta x1 multiplied with F1 is the virtual work done due to this force F1, and then virtual work done due to this force F2 on mass M2 is written here, that is F2 into its virtual displacement is delta x2. So again, comparing with the previous expression for virtual work given in the Lagrange's equation, we have two generalized forces Q1 and Q2, and that they are equals to F1 and F2. So we substitute all these quantities in the previously mentioned Lagrange's equation to get the final equation of motion. So in this slide, at the bottom you can see these two equations. These two equations are the equation of motion of this 2 degree of freedom system. So after this discussion for 1 degree of freedom system and 2 degree of freedom system, spring mass system, we understand one thing, that for 1 degree of freedom system we have one equation of motion, 2 degree of freedom system we have two equation of motion, and in both the cases we have not drawn any free body diagram. We have not shown what are the forces exerted by the spring, or what are the force or other forces. We need not to consider all these vector quantities. We have just calculated, we have just determined what is the kinetic energy and potential energy of the system and the virtual work related to this external forces. Then we have substituted all these quantities in the Lagrange's equation of motion to get the final equation of motion. So next, moving to the next example. This is again this is a single degree of freedom system, which I have already mentioned. In this single degree of freedom system, as I have mentioned, the rod is massless. We need only one quantity, that is only one coordinate theta 1, to completely specify the position of this mass m1. There is some torque which is acting at the hinge point tau 1, and this is under motion. So first, let us write down what is the Lagrange's equation of motion. Below this figure, I have written the Lagrange's equation of motion. Again, this is a 1 degree of freedom system, so we will have one Lagrange's equation of motion, and this Lagrange's equation of motion, the coordinate, generalized coordinate that we are using here is theta 1. So derivatives of Lagrangian we need to calculate derivative of Lagrangian with respect to theta 1 dot and theta 1. And what is the generalized force related to this torque, externally applied torque, which is acting at the hinge point, that need to be determined. First of all, what is the kinetic energy of the system? Kinetic energy of the system you'll get is half. Since this is a point mass, there is no rotation of the point mass. So kinetic energy is defined just half m is velocity square. So what is the velocity of this mass? Since the angular velocity of this rod is theta 1, so any point which is at L1 distance away from the hinge point on this rod will have velocity L theta 1 dot. So the kinetic energy is half m1 L theta 1 dot square. That is the kinetic energy of the system. And what is the potential energy of the system? Now in this case, what is the source of potential energy? There is no spring or restoring element is not there. You can add any restoring element, and if you add a restoring element, you have to take care of the potential energy due to that. Now in this case, the source of potential energy is the gravitational potential energy. This rod, this massless rod, and this mass is rotating under gravity. So there is a force acting downward. Due to that, there is some potential energy, gravitational potential energy, and we know that that is given by, I did a mistake here. So this is not half m1 gl sine theta. This will be m1 gl sine theta. Please correct. This is m1 gl sine theta. B equals to m1 gl sine theta. Okay. Let me check. Yes, this half will not be there. So you must correct this. This will be m1. M1 is the mass g, and what is the height from the hinge point? Vertical height is L sine theta 1. Okay, so we have chosen here the zero potential energy line is the horizontal line passing through hinge point, that is V0 point. From this V0 point, the height of the mass is given by L sine theta 1. So it will be m1 L sine theta 1. This half will not be there. Okay. Then the Lagrangian is defined as T minus V. So kinetic energy is given there, and potential energy. Remember that this half will not be there in the potential energy. That has to be corrected. And then take the differentiations of the Lagrangian with respect to theta 1 dot, and then they take the time derivative that gives you this m1 L square theta 1 double dot, and the derivative of this Lagrangian with respect to theta 1 equals to mgl cos theta 1. Here I have somehow corrected that was a mistake, typo. Okay, this is minus mgl cos theta 1. And you then what is the non-potential? What is the virtual work done by this externally applied torque? This is the torque multiplied with virtual displacement of the this is delta theta 1, and then the generalized force here is equals to tau 1. One thing I want to mention here is, let us go back to the Lagrange's equation of motion, where we have first introduced Lagrange's equation of motion. So this is the Lagrange's equation of motion. This equation of motion, although we are calling this QJNC, is a generalized force, but this can be a force, this can be a moment. Okay, this can be a force, this can be a moment. The same equation will give you a force equation, the same equation can give you a moment equation. When this is a moment equation, you will have this generalized force is nothing but moment. So in general, this is called a generalized force, but this can be a moment. So coming back to our discussion, this is a single degree of freedom system. In this single degree of freedom system, we have calculated all the derivatives, we have calculated the generalized force. Now substituting all these quantities into the equation, we get the final equation of motion. At the bottom, I have mentioned here, you just substitute all the quantities in this Lagrange's equation of motion, so you get this equation of motion. This is the equation of motion for this system. So dynamic model for this system is given by this equation of motion. Now let us